Now let's see the next point. I think you understood what is vector space and vector subspaces. And the last question was, what is the smallest vector subspace? The answer is 0 vector. So 0 vector satisfies both the properties of addition as well as multiplication. If we add a 0 matrices or 0 vectors, it gives 0 result, means 0 belongs to the vector and 0 belongs to that 0 matrix, and any value from minus infinity to plus infinity for C, if it is multiplied with that 0, results into 0. So already that belongs to our 0 matrix. So the smallest subspace is a 0 vector or 0 of any rank, r raised to 1 or r raised to 2 or of whatever the value of r. Now the next point we need to go for is, so that 0 subspace is the smallest one as it satisfies 1 and 2. The next point is the column space of A. So we need to learn what is the column space and the null space of any matrix A or whatever B of, generally let's consider A. Then the column space of any matrix is nothing but the individual columns. Is nothing here. Let's consider, to understand this one, let's consider a matrix as shown here. So of 3 into 2, 3:2 matrix having 3 rows and 2 columns. Now here we'll get 2 columns. 1, 5, 2 is the first column and 0, 4, 4 is the second column. The values can be anything, but here we can have 2 columns. So this matrix can be written as the sum of 2 columns or the combination of 2 columns. So which is referred as the column space. The column space contains all linear combinations of the columns of A, and it is the subspace of r raised to m. So here m into n is the order of the matrix, and we have this u and v. So here m, the number of rows are greater than the number of columns. M indicates the number of rows and n indicates the number of columns. As m is greater than n, 3 is greater than 2. Here we have 2 unknowns. They are u and v. They can be anything, x1, x2 like this. And 3 rows. The number of equations are more than the number of unknowns. So this equation can be written in this way. It is u is equal to b1, as we know how to write the equations from the matrices. So which indicates u is equal to b1 because 1, 0 into v it would be. Then 5u plus 4v is equal to b2 and 2u plus 4v is equal to b3 as given here. So this equation has 2 unknowns, u and v, and this matrix has 3 equations and 2 unknowns, and because of this it becomes impossible to solve, and the solution of this can be obtained if we express this one as the sum of linear combinations of columns. So the system will be solvable only for a very thin subset of all possibilities. A system Ax is equal to B, this equation, whatever, the matrix, whatever we have written, it is in the form Ax. Ax is equal to B form. So it is solvable if and only if the vector B can be expressed as the combination of columns of A. Then B is the column space. Now individual columns are written of matrix A. So first column and second column. First column and second column, and u is multiplied with the first column, the first variable, and second variable v is multiplied with the second column, which gives v1, v2, v3. Now, this equation can be solved in different ways. Let's see what is the solution of this. And if we go for, before going for that solutions, if we want to represent, as we know, here 1, 5 and 2. So this indicates what rank? It indicates the R3. It indicates R3. R3 has 3 components, as we already know, whatever may be the values. Now here the values are 1, 5, 2. The values are 1, 5 and 2. So it is R3. Each of this equation, each of this column space is of R3. Here, the representation of these points would be in this way. So these points are represented in this fashion. Now here, the axes are in this way. Axis means the points. This represents, let's say, the first value represents x, second represents y, and third represents z. If we consider in that way, if the first represents x, second represents y, and the third represents z, if we consider in that way, then our space is in this way. Now, this is, let's say, the origin, and in this way we draw. So this is positive x from this origin. So it is our positive value of x, and this would be the negative value of rx. The negative value of x, and this one is the origin. And let's say the right hand side indicates the positive y. It indicates y, and this indicates positive x. It is positive y, hence this would be the negative y, and the upper one, the vertical direction, let's say it indicates z. So the minus values would be below. Now, if we want to represent a point here, then the point is given by, let's say it is 1, 5, 2. Let's refer, it is 0, 0, 0. Of course, no movement in any of the direction. Certainly, it is the origin itself. Then 1, 5, 2. 1, 5, 2 can be represented in this way. 1, 5, 2. Let's have 1, 5 values in the 1 value in the x direction, 5 in the y direction, and 2 in the z direction. So which will be usually in this way. So we are representing that this way, this 1, 5, 2. Similarly, 0, 4, 4. 0, 4, 4 is represented. It is a 0, no movement about x. 4 means about y there is a 4 movement, and then 4, vertical 4. So which will be in this way. So if we draw the line from the origin, this represents that 1, 1, 4, 4, and this represents that this one is 0. This represents 0, 4, 4, and this represents 1, 5, and 2. I hope no confusions. Then let's refer the diagram given. So it is the origin, 1, 5, 2 is this point, and 0, 4, 4 is this point. Now, this is a diagram figure 2.1, the column space C of A, the plane in 3-dimensional space. So of course the plane diagram corresponding to R3. Then let's see the next point. The one possible right hand side is, like we are seeing the solutions of this. The solutions of this column space matrices. The solution of this one could be in this way. We can have the value of u as 1 and v as a 0, then the value of b1, b2, b3 will be 1, 5, 2. It would be 1, 5, 2. If the first possible solution is u can be 1 and v can be 0. If u is 1 and v is a 0, then if v is 0 means this column is not at all being considered. So b1 indicates the value of b1. b1 is equal to b1 is 1, b2 is 5 and b3 is 2. Similarly, the other solution can be just a reverse of it. Now u can be 0 and v can be 1. Then in that case, the value of b1, b2, b3 are nothing but these second column values. b1 0, b2 4 and b3 4. Then another possible solution can be u, v. They both are zeros, hence b1, b2, b3, they all will be equal to 0. So these three can be the possible solutions. Now, ax is equal to b can be solved if and only if b lies in the plane that is spanned by the two column vectors. The plane spanned by the two column vectors is this one. The plane spanned by the two column vectors is this one. So the plane, I hope you know, the ground is a plane and the table is a plane. So but we are considering an infinite dimensional plane here. A plane means which will be having the x in that direction from 0 to infinity, then y from 0 to infinity, and even z over 0 to infinity range. But it is for particularly these vectors. This is for the plane considered is for 152 and 044. Just seen in this fashion. So the plane consisting of these points and even the origin. So this is an infinitesimal plane. It's not just connecting these 2 points, it is a plane passing through these points but extending to infinity in all its possible directions in x, y as well as z. But it is not a particular x is equal to 0 or y is equal to 0 plane. It is a plane that is passing through these 3 points, that is all zeros, and that is origin, and all zeros, that is origin, and that 152 and 044. I hope you can imagine this one. Then the solution of ax is equal to b is possible. The equation ax is equal to b can be solved if ax is equal to b can be solved if and only if b lies on that plane. And means if it is lying over this range, it is there in this range. If it is not lying on this plane, then certainly it is not the solution of that ax is equal to b. It is not the solution of x is equal to b thing. Here, this plane is not just a subset of R3 because it can be referred as a subset because R3 can be any plane. It is one of the plane of that such to make R3 or R3 entirely is constituted by such infinite number of planes. So we can refer this ax is equal to b as a subset of R3. It is not just a subset, it is even the subspace. Because if we consider the sum of this 0, 4, 4 and 152 or generally anything, this 0, 4 0, 4, 4 or 1, 5, 2. It is a 0 plus 4 plus 5, 9 and 4 plus 2. It would be 6 something. Even that is there lying on this plane. Because we know that 1, there is 1, 4 and 5, 9 and 4 plus this 2. That is 6. Certainly, it has to lie on this plane. And even if any of this matrix is getting multiplied by any value like c is equal to minus infinity to plus infinity, any value, then certainly as per the properties of this plane, it lies on that. If c is positive, then it would be on the positive side. And if it is negative, then it would be on the negative side. But certainly it lies on that plane only. I hope as the planes are not perfectly known to you, it may be a bit difficult to understand, but certainly it lies on that plane. So it is a subspace 2. Now, requirements 1 and 2 for a subspace. As we know, the requirements are there. One is with respect to addition, the other one is with respect to the multiplication. So suppose if B and B dash lie in the column space. So if B and B dash means they are the solutions. Ax is equal to B and of x dash is the solution of Ax dash is equal to B dash. Then even A of x plus x dash is equal to B plus B dash is always true. Is also a combination of the columns. The column space of all attainable vectors B is closed under addition. So let's have a glance on this. So if we have A into X, so let's say our X is a three-dimensional one. So X1, X2, X3, giving B1, B2, B3. And similarly, A into X dash, this is our X dash is X1 dash, X2 dash and X3 dash, resulting into B1 dash, B2 dash and B3 dash. So which gives A of this A of x plus x1 dash, A of x plus x1 dash, A of x plus x1 dash, x plus x2 plus x2 dash, x3 plus x3 dash is equal to b1 plus b1 dash. So certainly these all will be lying on that plane. So x plus x1 dash. So x1 is some value, x1 dash is some value. The addition of that one has to lie on that plane itself. So it satisfies the first property. And if B is the column space of C of A, column space of A, so is any multiple of CB if some combination of columns produces B, Ax is equal to B, then multiplying that combination by C will produce CB. As we know that this plane is extending to minus infinity to plus infinity in all its possible directions in x, in y as well as in z. So if we multiply it by any value, if we multiply it by a positive value, let's say, then these would be shifted in the positive direction, but they'll be certainly lying on that plane. And if we are multiplying it by a minus value, because c can be anything from minus infinity to plus infinity, if we multiply with a positive value, they'll be there on the right side with the positive values of x, y, and z. If our column spaces, if the column is positive, and if we multiply it by a negative value, then certainly they lie on the negative side, but they lie on that plane itself. Because we know the multiplication is true for any of the, it may be a fraction or it may be any value. If we multiply them by a same value, then their ratio will not change. It is that kind of a thing. Then the next point is the null space. The null space of A. The null space of A is the null space of a matrix consists of all vectors x such that Ax is equal to 0. Means if we consider a matrix A or with any values of any value of m into n, then whatever is that Ax is equal to b, the x, it can be uv or x1, x2. The possible values of these unknowns which results into the zero results or the zero solutions of that Ax are nothing but the null spaces of A. The null space of A is nothing but n of A represented by Na, and it is the set of the solutions which give Ax is equal to 0. The solutions to Ax is equal to 0 form the vector space called the null space. The requirements for the null space are: if Ax is equal to 0 and Ax dash is equal to 0, then A of x plus x dash is equal to 0. And another one is, if Ax is equal to 0, then A of Cx is equal to. The requirements are Ax is equal to 0 and Ax dash is equal to 0, then this condition. And the other one is this one. So before going in deep with this, let's see a problem. Here, in this example, A is given by the same matrix, whatever we have considered, 1, 5, 2, a column matrix, and another one, 0, 4, 4, U, V. Then the possible values of U and V is 0, 0. If U is 0, V is 0, then only the result is 0. Otherwise, the result will not be. If U is 1, V is 0, the result would be this column. And if V is 1 and U is 0, the result would be this column. So here the result is a 0 if U and V are equal to 0. So 0, 0 is the null space. The first equation gives U is equal to 0. And even after solving this, if we go for solving this equation, so U is equal to 0 we get, and then 5 U plus 4V is equal to 0. As we know U is equal to 0, certainly V also will be equal to 0 after solving this equations. Then here we have only one solution, that is U is a 0 and V is a 0. So we can't go for the proving of this one, but we can prove it later and understand it when we go for solving these kind of problems. So the meaning of this one is, if A is there and X is there, which is one of the solutions, just like U is 0 and V is 0, which results into 0. And if another value of X dash means if there is some other combination, maybe 1, 0 or 0, 1 or whatever, maybe minus 1, minus 1, which makes this multiplication as a 0, then A multiplied by the sum of both of those values is equal to, like when we multiply this A or whatever is that matrix with the sum of these null values, then again the value resulted would be 0. And similarly, as we know that Ax is equal to 0, then C into x. Certainly, if we consider any multiplicative value to this one, the result is not going to change. It would be 0 only. So that is the null space. The null space of A is nothing but it is a set, or it is the space set of all the values which satisfy the condition Ax is equal to 0. The values for unknowns. For x, it could be x1, x2 or anything which makes the solution possible. The set of all those values. Now, the null space of this vector, this matrix is 1, 5, 2, 0, 4, 4. As we saw it earlier, it gives 0. Now, if we construct another matrix, let's say this matrix is A. Let's consider another matrix B. And if this B is having that same matrix plus the third column also, and the third column is nothing but the sum of the first and second columns, 1 plus 0, 1, 5 plus 4, 9, and 2 plus 4, 6. Then this is a 3 into 3 matrix. Then to have a 0 result of this one, to get a 0 result of this one, the values have to be what? The space set, the null set. The null space of this matrix could be what? So it has to be, like we know, the same values. It could be C, C, and minus 1. C, C, and minus C. It could be like 1, 1, minus 1. So you can check solving this one. So 1, 0, and minus 1 will make this entire first row as 0. Again, the 5 into 1 plus 4 into 1 will make it as 9, and minus of 9 will make it as 0. Hence, the null space of this matrix is 1, 1, minus 1. It is one of the solution. But we know that as it is this null space, it has to satisfy both of those criteria, A and multiplication A plus B as well as C into B. So if we multiply this solution with any of the values C, then this becomes C plus C, C, and minus C. So when we multiply this matrix with C, C minus C, then also the solution will not change. Even though if we take the two solutions, just like 1, 1, minus 1 is one of the combination. Similarly, 2, 2, minus 2 would be another solution, and the sum of them, here we can go for the sum of them. The sum of them means, let's say, C can be 1, 1, minus 1. Similarly, it could be 2, 2, minus 2. So let's write it in a bit comfortably. 2, 2, minus 2. Then also we'll get the result of that A into this value. Sorry, it is B into this value, and B into this value is always going to be 0. And when we add these two and then multiply it to B also, we are going to get it as 0. So these are the null spaces of A. I hope this point is clear to you. The next point, we'll see it later in the next video.